Okay, so good morning, everyone. Welcome to the Rec 9 webinar. Today's June 23, and we're actually glad to be today. We're glad to have Ian Vega with us, who will be discussing point particles in general relativity. So this promises to be a very fun talk from Ian. I've always enjoyed Ian discussing stuff, and this I think this would be the first time I would actually get to uh, grill him on his work. So uh, Ian is one of our really good professors in NIP. Students enjoy his classes, so this is gonna be a treat for all of us. So you have the screen, Ian.
Thank you, May, for the generous introduction. Thank you for the invitation from PAASE. It's my pleasure being here. Let me see if I can share my screen. Uh, okay, I think I need to go to slideshow. Uh, Wait, let me just. Oops, it does it automatically. I should not do that. Enter full screen na lang. Okay, so how's that? Do you see things? Do you see my slides, May?
I'm seeing goals of this
Gladys?
talk.
Yes, we're good.
All right. Okay. So, good morning, everyone. So again, thank you for the invitation and for the generous introduction. I'm Ian. I work at the National Institute of Physics. I am currently the coordinator of the NIP Theoretical Physics Group, and I lead the gravity subgroup that belongs. It's a subset of the Theoretical Physics Group. So if you're interested in learning more about the things I will talk about today, you can. I invite you to visit our website, which is right here. So today's talk will be about point particles in general relativity. I could have entitled this talk "My Adventures in Point Particles" with point particles, which reflects basically the common thread that runs through a significant fraction of the work that we do in my group. So I'm a relativist. So I work in gravitational physics, and so much of what I'll talk about today will be basically a showcase of some of the research that we have done over the past couple of years. So the thing you see on this first slide of mine is a typical representation of a curved spacetime meant to represent some kind of black hole here in the center, and a small, either a small neutron star or a smaller black hole that's sort of whirling around it.
I'm
And
sorry. We're not seeing that slide. I think
oh,
that's the slide.
so what slide are you seeing, May?
Goals of this talk.
Oh, how about now?
Still the goals of this talk.
Wait, let's see.
Okay, now we have it.
Let's see. Let me let me try that again.
It showed up right before you stopped it.
Yes, let's see. Hala. It went to the other page. Sorry, May. Just give me a second. This is the problem of having too many things open on your on your computer. I can't seem to find it. Okay, so how about now, May? Is that fine?
Yes, this is fine.
So I'll enter full screen. Does that work?
Yes,
Okay.
perfect.
All right. So right. So this is, as I was saying, this is the a typical cartoon representation of the kind of system that we usually work with. consisting of a larger black hole and then a smaller black hole essentially whirling around it. So so the goals of this talk are as follows. So I would want to first of all set the stage for our current work by reviewing some of the really incredible advances that have been made in general relativity. I will also talk a little bit about how modeling in gravitational physics and, well, classical field theory in general is done and the approximations that we make in order to make progress and to get insight. Um, Related to this, so what follows this will be an explanation of how point particle representations are used in this modeling endeavor, and and I'll explain basically how uh, point particles have been historically important, and pretty much all of the early applications of general relativity have made use of point particles in one way or another. And then finally, once all of that is set up, I'll finally begin to explain some of the contributions of my group. Um, so I'll start our story first by reminding everyone of Einstein's incredible theory. So in 1915, Einstein proposed his what was a radical theory of gravity and completely revolutionized the way we think about gravity. This is, of course, general relativity. And I say that it was a revolution because it really required a huge shift in the way one thinks about the gravitational force. So whereas in what had dominated gravitational thinking then and even to this day is the Newtonian mindset, where we consider gravitational interactions as resulting from a gravitational force between 2 point masses, right? So whenever you have 2 point masses, we always say, at least according to Newton's conception, that these masses are going to pull each other toward, pull them towards each other. And then that's that. And there's a lot of things that you can say starting from that premise. So one thing that is sort of missing in the Newtonian theory is the so-called what we now know to be the equivalence principle. The fact that somehow all the gravitational forces seem to be the same or act the same way on pretty much uh, all masses. And so this sort of gave Einstein the idea that perhaps gravity is not a real force, but rather a fictitious force coming from or arising simply because we are not in the right reference frame. So if you remember your early physics classes, probably many years ago, uh, whenever one works in a reference frame that's accelerating, then in the equations that you get, you will always get a fictitious force that is universal on all of the objects you're trying to describe in that reference frame. And gravity is of such a character, and you can always remove it, or any gravitational force in the way Newton described it can always be removed by going to the right reference frame. And so that was essentially the essential concept that led Einstein to his modern conception. And this modern conception treats gravity or gravitational interactions as manifestations of curved spacetime. So in other words, whereas normally we would think of the Earth going around the sun as a result of the Earth and sun pulling each other, now we don't think about that anymore, at least not in that way. We instead consider the motion of the Earth around the sun as as it trying to move in a straight line, in as straight a line as possible in the curved geometry that's created by the sun. And so there is this famous adage that sort of very well encapsulates the full physical content of Einstein's theory, which is, I think, is attributed to John Wheeler, where you have the space-time telling matter how to move. Space-time here being this sort of fabric, curved fabric-like mesh that you're seeing here, telling basically how the Earth is supposed to move around the sun. And then there's also a corresponding equation which tells space-time how to curve in the presence of these matter distributions here. Mathematically, these are encoded in the famous Einstein equations. So these symbols here aren't particularly important, but this is essentially expressing this connection between geometry, which is embodied by the curvature on the left, and matter content, which is encoded in the so-called stress energy tensor on the right. So this equation here is the second part of this adage about how matter is telling space-time how to curve. And on the other hand, this additional equation, which actually follows from this, is not a separate equation that one has to impose, is how space-time is able to tell matter how to move. So now, this was proposed in 1915, so it's been more than 100 years since this was proposed, and a lot of predictions have been made in the intervening years. What's interesting about GR is that although many of its predictions uh, came rather rapidly, many of these early predictions were mainly focused on the weak field, on a regime where gravity isn't particularly strong. And it's only in the past couple of years that humanity as a species has developed the tools, the capacity to actually test Einstein's theory in the regimes where it's most interesting. And this is the strong field regimes where gravity is very strong, where you actually get to see space-time being dynamical through many, and that's what I'm going to talk about in the next few slides. So many of you probably heard of the recent, well, I think I can still say recent, at least in the past 5 years, the discovery of gravitational waves. So gravitational waves are really undulations of space-time created by very dense, very heavy mass distributions that are moving or evolving in the cosmos. So the picture here is a cartoon representation of the kind of system that might generate such powerful detectable gravitational waves. On September 14, 2015, the very first gravitational wave was detected by the Laser Interferometric Gravitational Observatory that's based in Livingston and in Livingston, Louisiana, and Hanford, Washington. So this is a facility that consists essentially of two 4 kilometer arm. It's basically a 4 kilometer length interferometer. Basically, it shoots lasers down these pipes, and the main reason that that has to be there is because the gravitational waves that we are trying to detect tend to be very, very weak, and to improve our ability to detect them, we really need these very long arm lengths to be able to detect these very small effects. So the first one was, in fact, after more than 2 decades or 3 decades of effort, the first gravitational wave was detected in 2015. This is essentially what it looks like, the noisy signal that they got, but it was pretty strong compared to what people were typically expecting. This is a cleaned up version of it. And as you can see here, it's now being matched with a theoretical model coming from numerical relativity, and you see this exquisite match between theory and the actual signal. Uh, Another way of representing these so-called chirp signals is via this spectrogram that you see on the bottom right. So here, this is showing you basically the energy contained in the wave versus frequency and time. So this is a frequency time spectrogram here. So time moves to the right, frequency goes on the y-axis, and the color scheme here essentially represents the energy that's contained in these frequencies. And so this is a typical representation basically of the same signal that you see here. It's telling us that as time evolves for a system like this consisting of a binary black hole, you get something that starts with a fairly low frequency, right, with not much power because the black holes are still far apart. And then gradually, as these guys evolve and they continue to emit gravitational radiation, the orbit shrinks, therefore making them more energetic and also making them move faster. And so as time evolves, you get this evolution towards higher and higher frequencies. So you see here that the signal is kind of um, bunching up as it evolves, and then as it does so, you get more power emission, and you also get an increase in frequency until it stops and then becomes basically merges into a single black hole that's deformed, and then it oscillates a bit before settling into a quiescent rotating black hole. So this is precisely what was observed in September 14 in 2015. Uh, 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 just a few months before I had actually moved back to the Philippines. So nowadays, in the intervening years, we have had a plethora of new results. So here is our 90 spectrograms of pretty much all the sources that have been detected to date. So again, all of these are the same as the spectrogram of GW 150914. Some of these represent not just black hole binaries, but neutron star binaries as well. We've also seen them. And these are significant because they also released a corresponding signal in light. It wasn't just in gravitational waves. And I believe that these are the ones on the at the top, or some of these are at the top, and the rest are just are binary black holes. Now, again, I need to impress how significant this is because many of these sources would not have been seen if we did not have our gravitational wave detectors, right? Because many of these sources are essentially do not release any light. So if you're just talking about black holes and not neutron stars, black holes are really just pure space-time. So there is no light that comes from them. The only way they make themselves known to us is via the gravitational waves they emit. So in some sense, gravitational wave astronomy, which is this new way by which we perceive the universe, is a complement to optical astronomy. And usually, the way this is explained, the relationship between the two is explained is that so gravitational waves is kind of like hearing the universe as opposed to optical astronomy, which is about seeing the universe. And so I say this is a new era because, first of all, we are now able to observe many of these events that would otherwise be invisible to us. And now it's no longer, because I still remember my PhD days where it was all about getting down the noise curves, always trying to put a face of optimism to the whole effort and never actually making detections. And now over the past 5 years, we now are in this situation where we've had so many detections of gravitational waves. And so now the task will be to consolidate all of this information and try to make sense of it. And one of the ways to do this is by continually making these measurements, these characterizations, to get enough statistics to then that we are then able to um, confront, say, population synthesis models of how black holes grew as the universe evolved, to match them against a growing census of black hole masses and spins as it evolved in cosmic history. So that is ultimately what the goal of one of the ultimate goals of gravitational wave astronomy, and we are now at this stage. So now, it's not just gravitational waves that have been one of the main breakthroughs although even if it were the only breakthrough, that would be a very significant breakthrough. Um, so other than gravitational waves, there also has been, as you may have heard, the imaging of two galactic black holes. But before I get to that, I want to mention that although all of these efforts required many, many people, engineers, scientists of all sorts, and required very heavy simulations to make sense of it all, it's important to note that all of these breakthroughs began from rather humble theoretical beginnings. So here I'm showing you the first papers that Einstein had written about gravitational waves, and even you see here already things that I teach my students in my introductory GR class. This how he writes the representation of gravitational wave here is very similar still to the way I do things now. So this is so this I mean if I'm not sure if anybody here reads German, but this first paper was translates to approximate integration of the Einstein field equations, whereas the second paper was really where he talked about gravitational waves. But uh, yeah, as you can see here, this was in 1918. There's been the history of gravitational waves is also very rich. It's also one of those. It's a very interesting case in the history of science because it seems to be, if I'm not mistaken, one of the main predictions that really took such a long time to be confirmed, right? So most predictions, theoretical predictions in science, uh, have a shelf life that doesn't well, probably a shelf life of about a decade, whereas gravitational waves took about 100 years, and yet still, it didn't actually die out. And people were consistently propping up the possibility that we would detect it, and eventually we did detect it, and so yeah, so it's interesting in that sense. So like I was saying, other than gravitational waves as our probe to binary black holes, the other rather incredible and astonishing development has been our ability to image the neighborhood of galactic black holes. So now, you would be right in thinking that these black holes are really quite big objects, but they are very far away from us. And so, these represent, so the ability to image their vicinity is really quite a challenge for astronomers because we're talking about very, very tiny objects in the sky. So these are around 30 to 50 micro arc seconds. So one way to think about an equivalent angular size would be like putting a donut on the surface of the moon and trying to image that donut from the moon. So this is the kind of thing that they've been able to achieve in um, uh, uh, over the past couple of years. Uh, what led to what was a precursor to these developments was the work by two groups primarily to try to look at uh, these so-called S stars, which are big stars that are going around an invisible center in Sagittarius A star. Sagittarius A star is our galactic black hole in the Milky Way. And so here you see the evolution of some of these stars. One favorite of mine is this S2, which is a very tight orbit. It's relatively relativistic. And they've been tracking these big stars for more than a decade, and they're still many of these surveys are still ongoing now. And in being able to do this, people like Andrea Ghez, or Nobel laureate Andrea Ghez, who leads this UCLA group, have been able to put estimates on the mass of our central black hole. So this is quite impressive because prior to this, our observations of black holes mainly consisted of looking at AGNs. So AGNs are so-called active galactic nuclei, which are basically black holes that are being fed gases and shine very brightly as a result. Some of these AGNs are also typically some of them are also known to be producing these relativistic jets, okay, which are basically energetic charged particles that are very highly collimated, that they move at relativistic speeds, and these are hypothesized to be moving along the rotation axis of black holes. So it's important to understand that over the past decades, um, pretty much every galaxy that we observe now is believed to have a central black hole. So this is kind of like the prevailing narrative that there must have been a connection between black holes and galaxies and galaxy formation. And so these were early works, very impressive works that sort of firmed up, established the notion of black holes and their relevance for astronomy. There used to be a time when black holes were really figments of a theoretician's fancy, and astronomers were pretty much ignoring this. But over the past couple of decades, it's become canon uh, uh, in astronomy. And so these are the kinds of pictures, the two famous pictures that you're probably aware of. The top part is an image of M87 that the Event Horizon Telescope collaboration put out in 2019. And just very recently, they've also been able to achieve something very similar for our very own black hole Sagittarius A star. Sagittarius A star was much more challenging to image, although it is slightly bigger in angular size than M87. M87 actually is a much bigger black hole compared to our own black hole, but its angular sizes are similar because M87 is significantly farther away from us. The reason Sagittarius A star proved to be a challenge and took some years before they could release this image was because of the gas, the intervening gas and dust between us and our own black hole, right? Because so both of us lie on the plane of the Milky Way, so madami. So there are lots of things that they had to contend with in order to actually get this image. Whereas M87 does not lie along the plane of the Milky Way, so it was easier relatively to image. So this Event Horizon Telescope collaboration is quite an impressive collaboration. The only way they could have achieved this was by creating effectively a telescope out of the entire Earth, and the way they are able to do that is by essentially gathering or connecting data from many different telescopes. So there was no single telescope that could have produced this image because these are just very small compared to what we can possibly view. But with clever optics and clever data analysis techniques, what they could do was combine all these different telescopes to essentially create a telescope with an effective aperture that's basically the size of the Earth. And so now, so why is this important for gravitational physics? It is impressive as a feat of optics for sure, of instrumentation, but it's important because it opens a possibility of actually testing the so-called black hole hypothesis. So there remains a question of whether or not the black holes that astronomers observe, the black holes that they see in the sky, are indeed described by the solutions of Einstein's theory. And so now, by looking at these images and characterizing them further, this provides us a unique opportunity to perform these tests. So, yet again, I emphasize that although many of these advances were fairly intricate, requiring many simulations on large scale superclusters, supercomputers. Um, Much of this work began from simple considerations. So I like showing this image by Luminae because these images that you see here were actually hand drawn. Okay, so the data so the kind of images that they were able to produce in the 1970s, which is really what started this line of investigation, were all because they were numerically computed, but they were hand drawn. So this is the kind of thing which this is what's known as a black hole shadow. This was done by James Bardeen many years ago, and they were the ones who really started this line of investigation. So again, the point here is that much like the early work of Einstein, all of these incredible advances began with very simple relatively simple theoretical considerations. And I make that because and from that, we are now in this situation where Nobel Prize are finally being awarded to advances in strong gravity. So very recently, you probably have heard that the Nobel Prize was awarded for black hole physics just in 2020, and a few years before that, it was awarded for gravitational waves. Prior to these two discoveries, or these two awards, there were like GR related awards. So Chandra famously received the Nobel Prize for his early work on degenerate stars. He wasn't actually very happy about this. I mean, he wanted to get the award for what he considered to be something more substantial. Um, And then there was of course Hulse and Taylor, who had discovered a pulsar system that in some sense was not in some sense in a very real sense was the first strong field evidence for the emission of gravitational radiation. So the pulsar that they saw was one that allowed them to track the decay of the orbit in time, and which they were able to match precisely with what Einstein had predicted. So that was really the first indication that gravitational waves and the emission of gravitational radiation was a real thing. But it took some years before the Nobel Committee began awarding these awards to the Nobel Prize to strong gravity discoveries. All right, so there are two lessons I think to be learned from this. I kind of want to emphasize, given the potential audience. So that even though we are in this sort of now golden age of gravitational physics, with large-scale programs involving many people, engineers, theorists, experimentalists, none of these incredible advances could have been possible without the earlier theoretical work that were done by the greats, right? So Einstein, Bardeen, etc. And so there was a lot of theoretical work. Some I can't possibly list them all, but there was very important theoretical work that served as the foundations for these advances. Another important point is the importance of of theory and modeling in many of these endeavors, right? So, and I suppose this is it's a fact of life that when our instruments, when what we can directly see or hear is no longer enough. To extend our reach, we need to do clever modeling for us to make sense and to actually tell us what we expect to see, and then when we see them, to be able to interpret them meaningfully. So I offer this as a call to science administrators and funding agencies. Please don't forget us theorists, because I'd like to think that we do make important work, and after all, we're quite cheap compared to everybody else, funding wise. So, now that with that out of the way, I'd like to spend a little bit of time explaining how we do modeling in general relativity. So there are two classes of problems that we encounter in relativity, and in fact any kind of classical field theory. So the first kind of problem is the first kind of problem is when you sort of know what the space-time geometry is. Maybe you know, for example, that you have a black hole, and that you can sort of more or less say, if it's not spinning, that it might be a Schwarzschild black hole. If you know what the geometry is, often the problem becomes understanding how stuff or matter moves around that space-time geometry. The other sort of complementary problem is knowing what the source is. So maybe you can have a point particle, as I've said, or maybe you have a fluid. You can then consider or try to determine what the space-time geometry is generated by such a source. So by stuff and geometry here, so stuff here means basically all the matter fields you can think of. Typically, these are fluids, but it can also be electromagnetic fields. And the sources I'm going to talk about today, as indicated by my title, are point particles, which are very useful approximations to very complicated stuff that that exists in the universe. Now, and by geometry here, I really mean a so-called metric. A metric is just an object that allows you. It's a theoretical device that allows you to determine distances between events in space-time. So this is what we mean. So this is the geometry is what was represented by the fabric that I showed you a few slides back. So now mathematically, those of you who are aficionados here will recognize. So this is I'm schematically representing what these equations look like. The equations are a whole lot more complicated than what I'm showing here, but this is already telling you effectively how difficult these problems are, and these problems are really difficult because they are inherently nonlinear. Nonlinear in the sense that So you have your unknowns coming in not by themselves. So for example, here G is the so-called metric. It does represent the geometry of the space-time. And the equation that governs it, so this is the appropriate equation here, it's really a PDE where G appears nonlinearly. So you have G multiplying G here. And such partial differential equations are incredibly difficult to solve. So this is the equation that sort of tells us that if you have matter represented by this T here, you solve this equation to determine uh, what the space-time geometry is. On the other hand, the thing on the left uh, is a schematic of basically knowing what this G is. This will tell you basically how your matter fields, represented usually by a density or a pressure, will evolve in this given geometry. Now, both of these problems, if you solve them separately, is of course a cheat because to really get uh, a perfect or correct description of what's going on, they have to be solved simultaneously. And in many of the interesting situations that we encounter now, like say for example, looking at hydrodynamics in the vicinity of black holes, you can't get away with having to solve these equations simultaneously. And so these are very difficult, and so this actually has opened up an entirely new field known as numerical relativity, which basically is the field that studies techniques for solving these equations simultaneously on a computer. But I'm not going to talk about numerical relativity now because I don't do it, and at the moment we do not have the capacity to do it. Although one of my PhD students is trying to get into the game, but I'm going to talk about a different approach to sort of making sense of these equations, in spite of rather drastic simplifications that we make, right? And so this is where point particles, which is the main point of my story today, comes in, right? So what are point particles? So point particles are really simplified descriptions of localized classical matter. And the way we represent it, at least pictorially, is by this world line here. So you think of a point particle as basically a structureless object. All of us in one way or another can be simplified to a point particle. Like if we only care about our own position and how we move in space-time, then as we evolve in time, we will trace out essentially what's called a world line, right? Basically, this giving us a position that evolves in time. So this is a very simplified description uh, 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 of matter fields that can be very complicated. So, I mean, something slightly more complicated than a world line that's sort of still useful these days because of string theory. You might think of extended objects that trace out a world sheet in time, or if you're thinking about really extended distributions of matter, then this will trace out what would be a world volume. So here in this picture, I'm calling this a brain, but this could be really any three-dimensional, any extended distribution of matter. The representation using point particles is quite useful. It remains quite useful, and the reason it's still being used today is because it's not a bad way to start to gain insight from the Einstein equations. Whenever whenever you expect your matter distribution to have a length scale that's significantly shorter than the curvature length scale of your background spacetime. And so this turns out to be important in a number of applications, and in the applications that I will show you in the next couple of slides. So examples of this, which were historically important, are, for example, include, for example, the motion of planets around the sun. So the planets are far smaller compared to the curvature length scale that's generated by our larger sun. Or, like if you can look at photons, for instance, moving around a black hole. So if these photons are, the length scale of these photons are given by their wavelengths, and if you look at very high frequency and others very short wavelength, photons, you can treat them essentially as point particles moving in a say in a black hole space-time, for instance. If you were to perform these ray tracing calculations that were done for the imaging of M87 and uh, SGR A star. Uh, right, so this is going to be the focus of many of the applications I will talk about next. So just to put a little bit more math to our description here. So point particles, I mean, like I said, they are represented. They do come with a stress energy tensor, and these are the things that appear on the right-hand side of the Einstein equations. They are represented by these, delta function representations. And the nice thing about them is that when they are incorporated into the Einstein equations, their equations of motion reduce to something far simpler, which are known to be the geodesic equations. So I put them in quotes because these equations still represent rather difficult nonlinear ordinary differential equations that you still have to analyze in order to make sense of. But this is far easier compared to the partial differential equations that the Einstein equations are. So this test particle approach, where you only consider point particles, as I see here, has been used since the very early days of relativity. In fact, the anomalous precession of the perihelion of Mercury, which was the first major result of GR, was just largely based on geodesic motion. This is something that I derive in that you will encounter in any elementary general relativity class. So, so here is a cartoon of this perihelion, the precession of perihelion of Mercury. For centuries, although one of the challenges that Newton's theory could not predict was how the orbit of Mercury around the Sun precessed in time. So we know from Kepler's laws that the planets go around ellipses, right? These ellipses actually precess, they move also in time, but if you were to take into account only Newtonian theory could not match exactly what was observed to be the precession of Mercury, and this required a general relativity correction to finally make sense of, to finally get a perfect match between theory and observation. So this is one example of a success of the success of the use of point particles in relativity, and this was again, like I said, the earliest prediction, successful prediction of GR. It was really not a prediction, but a post-prediction to some degree, because they had already known the anomaly, and Einstein simply had to, well, simply is probably not the right word, but had to derive that anomaly from his equations. Um, Another more recent example is fairly common these days, which is ray tracing. So a very useful calculation that's been something that's done, for example, in the theoretical work for the Event Horizon Telescope is by looking at the orbits or trajectories of photons around black holes and determining from that what images we're supposed to expect from sources we expect from sources that are reasonable or that we might expect in the neighborhood of black holes. So this is this is again another example where point particles in GR remain quite useful. So our own work here is motivated. So, oh, sorry. Before I get to that, there is a caveat to using point particles in GR. Uh, uh, Already in 1987, a now classic paper by Garrosh and Trashen warned us that the use of these world line distributions is in fact quite invalid, and which is a surprising result considering that as I've said, point particles had been used for many, many decades before the 1980s, ever since the introduction or the discovery of Einstein's GR. And intuitively, one can think, one can make sense of this warning by the fact that if you consider, these point particles, because they have finite mass and they're somehow restricted to a zero volume, GR already tells us that such an object cannot exist because they should have collapsed into a black hole already. But more technically, uh, 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 such distributions in GR are not allowed because the nonlinearity of Einstein's equations sort of invalidates standard Schwarzian theory of distributions. So this needs to be generalized, and there are attempts to actually generalize this to so-called Colombo algebras that make sense of products between distributions, which is not present in the standard distribution theory. However, point particles are okay whenever we're dealing with the linearized version of the Einstein equation. So one of the ways one can make sense of the very complicated Einstein equations is by linearizing this, essentially looking at assuming that you have some kind of background and then just looking at perturbations on top of this background. And so this very, very complicated equation gets reduced considerably if you make that approximation, and so one has to deal with just the so-called linearized Einstein equation. So for such a linearized Einstein equation, world-line distributions are okay, and this has become the basis of many theoretical works, including the work that we do in my group. So now, contemporary work, more modern work, making use of point particles in GR has focused or can be categorized into two classes. So one that I'll talk about in the next few slides concerns astrophysically important corrections to the motion that would be there if you just simply assumed that they were test particles, or geodesics. So geodesics, maybe I haven't emphasized this enough, are really just the analogs of straight lines on our flat geometry. So when you draw straight lines on a flat plane, those are geodesics on that flat plane. But what is straight will be different depending on what the geometry is. So if you have if you're looking at a two-sphere, say for example, or a globe, then straight lines there are not straight anymore. What straight lines are would be the great circles. And so again, like I say, so these geodesics are generalizations of straight lines, and they are so the simplest kinds of motions that are traced by these test particles. And much of the work now concerns looking at important contributions or corrections to this kind of motion. Another line of work is focused on characterizing or discovering novel behavior arising from the fact that um, uh, generally point particle motion tends to be chaotic, and so there's always this question of looking for chaotic signatures in the motion that's traced by these concentrated distributions of matter. Both of these things we are pursuing in my group. So uh, so let me set up what will be the I wouldn't say a successor, but it's an effort that uh, will definitely complement the success of LIGO and will further extend the reach of gravitational wave astronomy. So LISA, or the so-called Laser Interferometric Space Antenna, uh, is a proposed ESA NASA project consisting of these three satellites in this triangular configuration that will track the orbit of the Earth and go around the Sun. This is kind of like an analog of the LIGO detector, but it will be flying in space instead. By flying things in space, we will allow ourselves arm lengths that are significantly longer than the 4 kilometer arm lengths of LIGO. Because of this, the longer arm lengths allow us to probe uh, uh, gravitational waves of much lesser frequency than the ones that we are able to see at the moment. And these low frequency gravitational waves are so important because many of the important sources of gravitational waves do have very low frequencies. So my favorite source, my favorite system, is the so-called extreme mass ratio inspiral. So this consists basically of small objects like neutron stars or white dwarfs, falling down the galactic black holes that are at the centers of all galaxies. Um, so these are known to be, I mean, we at least expect them to be copious emitters of low frequency gravitational waves. So, and these are going to be very important because this is, if we do detect such an emery, this will provide us a far more exquisite test of Einstein's general relativity than any of the tests that we've had to date. Because this will allow us to really probe the geometry around these black holes uh, to much higher precision than we've been able to achieve to date. For this to succeed, however, uh, um, much theoretical modeling needs to be done because unlike, I mean, if the LIGO facility already suffers from a considerable amount of noise because of all sorts of things like seismic noise, for example, or just shot noise from their lasers. The noise floor for this LISA satellite will be significantly higher, and so the demands for better models, more accurate models, and extending many cycles for many time scales, in other words, is significantly higher than what LIGO requires. And on top of that, the sort of Emery orbits, these extreme mass ratio in spiral orbits, are far more complex than the binary orbits that LIGO currently is interested in. So for an Emery event, you get orbits that are very complex. So here is an example of a kind of orbit moving around a Kerr black hole, which is a spinning black hole, and you see here it's very intricate. And compared to the signal that I showed you a few slides back, you see here that you have all sorts of modulations arising from, I mean, this would be the representation of a gravitational wave coming from a source that looks like this. So as the object or as your small black hole goes in spirals or moves around your bigger black hole, it will emit gravitational waves that are of a substantial complexity compared to the ones that we're seeing with LIGO these days. And so not only that, it's not only the complexity that's the challenge. It's also important that theoretical models for LISA uh, stay, are able to track the motion over 10 to the 5 to 10 to the 7 cycles. So LISA will fly for a number of years, for about 5 to 7 years. And so if you think about year as a typical dynamical time scale for these orbits, the small mass has to be tracked accurately as it moves around it over this many orbits. And so for such, because of this, it is not sufficient to just look at test particle motion. One really has to consider the effects of so-called radiation reaction and self force. And so this is what I was talking about earlier about important corrections to test particle motion that need to be incorporated into our models for us to succeed in this endeavor. So what are self force and radiation reaction? So self force is a more modern term, but some of you may be familiar with the phenomenon of radiation reaction. So this is simply this phenomenon whereby if you have a particle, so typically we encounter this in classical electrodynamics, where you have a point charge, for instance, and if it accelerates, it emits radiation. Because it emits radiation, it has to lose energy, right? And this loss of energy manifests as a slowing down or a braking on the motion of your charged particle. So something, a more general effect is what we know to be the self force, because radiation reaction, the effect of emitted radiation on the motion of the particle itself, this really is just the dissipative part of the self force. Dissipative because it's time. If you reverse time, then you reverse the sign of this self force or this radiation reaction. If you reverse time in that process that I just said, then instead of the object slowing down, you get a situation where it's actually speeding up, right? So that's the so-called dissipative part. The self forcing will have a dissipative part and a conservative part, and that's what we call to be the self force. So this self force really just represents the interaction between the particle and in its own field, and this is something that arises whenever you have any particle really being able to generate either an electromagnetic field or any field for that matter, right? So the thing that we're familiar with typically is, like I said, a charged particle that's emitting radiation. But this is a situation that we will also encounter when you have a point mass emitting gravitational radiation, or in fact, even a scalar charge, which is a hypothetical charge emitting scalar radiation, will also experience a similar cell force. Now, the thing about this cell force is that, first of all, it's rather difficult to calculate, and this has motivated a lot of hard work or effort in trying to actually perform these evaluations, and more than that, cell force is also rather difficult to predict ahead of time because they tend to be rather unintuitive. So without actually doing the calculation, it's very difficult to guess what the form of the cell force is. In fact, even the sign of the cell force becomes is rather difficult to guess without a proper calculation. So this cell force, so this is just to show you, what the very first representations of these cell forces were. I like to show this because just to highlight that the difficulty in calculating them comes from the fact that we actually have to integrate over the entire world line of the particle. So even though these are already simple representations of sources, accounting for this cell force or corrections to test particle motion becomes difficult because you have to perform this highly non-local integral in order to perform its evaluation. Though of course there are now better ways to evaluate the cell force, but uh, 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 this captures essentially the gist, I think, of where the difficulty lies. So the Misatakuwa equations are named after, if this is a funny name, but they're named after the people who derived these equations originally. So this is Mino, Sasaki, and Tanaka, and Quinn and Wald. So they somehow merged all their surnames to turn out to make this name for the equation, and somehow it has stuck all these years. So so I'll just show you a couple of examples where we have succeeded in making contributions to this endeavor. So ultimately, the goal of the community is to perform or to produce what are called self-consistent, self-forced motion for extreme mass ratio in spirals, and that this has to be correct up to second order in the mass ratio. So this is still an open problem to this day, and a few of my friends are very hard at work trying to pursue this goal. So very early on, so this is actually part of my PhD, uh, my collaborators and I were able to do this to some degree for a toy model consisting of a scalar charge. So a scalar charge is really just a point mass, a point particle that's emitting scalar radiation. This is a toy model, it's a simplified version of the actual thing, but what was significant about this is that we were actually able to produce self-consistent simulations that incorporate self force into the motion already. So here is an example of some of our results. If you look at, for example, a scalar charge that's moving around a black hole, a Schwarzschild black hole in this case, a non-rotating black hole, you get this fairly nice motion that's on the bottom left of your screen. But then if we turn on the scalar charge and incorporate the cell force that's acting on the motion, then you get this far more complicated looking trajectory, right? And so here we artificially made the scalar charge rather big. Strictly speaking, these values should be fairly small if it were to be a good representation of emery motion. But we did this so that we to essentially illustrate the effects of cell force much more strongly. One other way of describing or representing this kind of a motion or the effects of cell force is by looking at considering the orbit, the trajectory of the particle in terms of an ellipse, an evolving ellipse. You can think of this regular motion that you see here as being an approximate ellipse at any given time. And if it can be represented as an approximate ellipse, then it can be represented by the eccentricity of the ellipse and the semilattice rectum of the ellipse. So so think of it as an evolving ellipse you can think of this motion as essentially snapshots or as basically an evolving ellipse at any given time. That's usually a useful description uh, for this uh, for this evolution. Now, without these cell force effects, on this eccentricity semilattice rectum plane, um, uh, uh, something that looks like this, where you have no charge, no scalar charge, will remain basically a point, will be a single point on this plane. But as a result of the cell force, you see that the eccentricity, for instance, for certain values of the scalar charge will be evolving in time. So this is actually an evolution in time in this eccentricity semilattice rectum plane. So not only is the orbit becoming more and more circular because you have a decrease here in at least in these in some of these you should look at the purple curve here because it's closer to what really happens in reality, because this is the smallest case, that it's the smallest Q that we did. You see here a gradual decrease of eccentricity, which corresponds to a circularization of the orbit. The orbit becomes more and more circular because of the emission of scalar radiation. While it's doing that, it's also decreasing its semilattice rectum. In other words, its orbit is becoming tighter and tighter. So it's shrinking essentially as it approaches the black hole. Eventually, this will cross the so-called separatrix. The separatrix really is this line that separates bound elliptical motion from these points here, which represent plunge. So the moment it crosses this line here, the orbit no longer becomes an approximate ellipse, but rather it just goes directly down the horizon of the black hole in one dynamical timescale very, very quickly. Here is the bottom plot here is essentially the same thing that you see here, but for much smaller scalar charges. And what's interesting about this is that we see that instead of the orbit becoming more and more circular, you have an increase in eccentricity in time before it plunges down the black hole. So this is a kind of model that we would like to be able to produce, but albeit much more accurately to second order in the so-called mass ratio, which is which would be the equivalent of this scalar charge in the actual non-toy model problem. All right, so this was something that we had produced very in 2009, so some years ago. My group has tried to make contributions to the cell force work um, in various ways. So one of the things we have been interested in is by considering cell force in alternative theories of gravity. So this is important because many problems remain in gravitational physics. One standing question in spite of the successes of Einstein's gravity, uh, is whether or not Einstein's GR is really the correct theory of gravity describing all gravitational phenomena in the universe. One of the ways we can tease apart these alternative theories of gravity from Einstein's general relativity is by considering alternative black hole solutions arising from these theories. Unfortunately, many of the black holes in alternative theories happen to also be solutions to Einstein's GR. So one has to be a bit more creative about looking for ways to discriminate between the solutions. And so one possibility is by looking at cell forces in these alternative theories of gravity. So in this work with a master's student, Jezreel Castillo, which we published in 2018, we considered the possibility of calculating cell forces in it's a peculiar theory of gravity. It's no longer very popular these days, known as conformal scalar vacuum gravity. So the only reason we were interested in this theory of gravity is because it actually it had a hairy black hole solution. So this is the metric of the black hole that solves the equations of gravity in the field equations of this theory of gravity. And this kind of a black hole solution actually harbors a scalar field, which is what we call to be hair. This is a non-trivial hair that's living on this black hole. This line element, this metric, however, is in fact identical to a charged black hole solution in Einstein-Maxwell theory. So in other words, Einstein's theory with Maxwell's equations built in. If you had an electromagnetic field, um, uh, uh, outside a black hole, then you would have to solve the Einstein-Maxwell equations. So this solution is in fact very similar to a well-known solution in Einstein-Maxwell theory, which represents a charged black hole, and this is known to be the Reisner-Nordstrom solution. This solution becomes this when you simply let Q, which is the charge of a black hole, be equal to the mass of the black hole. So you can just squint your eyes a little bit and see that this, if Q equals M, this becomes equal to this line element. So we thought, well, okay, instead of going directly to this peculiar solution, we might as well just do self-force calculations in this more general class of solutions. And so we did that. And one of the interesting things that we got from this, well, first of all, we got to correct some Positonian results. We found that, so when we computed this cell force and compared it to some analytic results in the Positonian in the literature, calculated analytically via a Positonian expansion, we found that the Positonian expansion was actually incorrect. So and so we pointed that out, which is kind of a nice thing to do. But more importantly, one of the surprising things we discovered from this work was this so-called quenching. So we have here a black hole, and you have a scalar charge essentially moving around it. And what we noticed was that as this epsilon, which represents it's an extremality parameter, so it measures basically how far away from being an extremal black hole this black hole is. So when cube equals m, this exactly becomes the BBMB black hole that I showed you here. So it basically represents the deviation away from that solution. We notice that if you look at this plot here, as epsilon goes to 0, we also see this fall off of the energy flux. So E dot minus here represents the amount of energy that falls down the horizon. This gradually goes to 0. In fact, we were able to characterize this as a 5/4 power law as epsilon approaches 0. So what that means basically is that the horizon, as opposed to being something that always absorbs energy, essentially gradually becomes more and more opaque as extremalities approach. So when you fully get to this fully extremal state, the horizon essentially shuts off. It no longer absorbs energy. So that was an interesting result that arose from. It was one of the interesting results that arose from our calculations. Another similar line of work along the lines of extending what is known about cell force is work that I'm doing with a PhD student of mine, Adrian Villanueva. So this really tries to answer the question of how cosmological expansion might affect cell forces, might affect motion around a black hole. So it turns out that we have an exact solution representing a black hole immersed in an expanding universe. If you consider the expansion of the universe to take place in a time scale that's much longer than any of the dynamical time scales characterizing the orbits around the black hole, then such a space-time can be well represented by the so-called Schwarzschild de Sitter space-time. So it differs from the Schwarzschild space-time. So this is a black hole in which you have the mass of the black hole being m, and you have the so-called cosmological constants, which really represents the expansion here, carried by this lambda that appears in this metric. So we have rather tight constraints on what this cosmological constant is. So it's actually quite small. So in reality, this term is very, very tiny. So these effects are at most, can't really be expected to be observable in any real sense because of the sheer smallness of this lambda here. However, we are pursuing this because there are actually many things that might give rise to an R squared correction to the Schwarzschild metric. So it need not really be a cosmological expansion that's producing these corrections that you see here to the space-time. One can also contemplate maybe, tidal effects. You can think of an accretion disk far away from the black hole that might be inducing this r squared correction to the metric. And so, not it's this calculation that we decided on pursuing is not really just for a situation where we have a black hole immersed in an expanding universe. It can stand for many things. But the overriding question was to understand, how these different effects, cosmological or tidal, might impact extreme mass ratio in spiral dynamics and waveforms. So here are some of our partial results. So this work is still largely in preparation. So we haven't quite finished it because it's a fairly long piece of work. We're now running into 30 plus pages of our manuscript, so it's rather difficult to organize in a nice way. But one of the nice things about one of the interesting results from our work is that you get the space of bound orbits reduced because of the cosmic expansion, because of this additional term in the metric. So this is very similar to the eccentricity and semilattice rectum plots that I showed you earlier. Again, bound orbits are represented as approximate ellipses that evolve in time. So the thing that you see here, so if there were no cosmological expansion, then this straight line that you see here is what represents the separatrix, and all orbits, all points to the right will represent bound orbits. What we see is that when you include this correction, you get an additional boundary that which is represented by this curved this dashed curve here that restricts the possible bound orbits. So instead of getting all the points to the right, you only have these possible eccentricities and semilattice rectums representing bound orbits for such a system. Um, so this is pretty similar as well. So this, on the other hand, represents uh, so for this plot on the left, we're actually considering the things outside the boundaries that you see here represent those that already plunge, whereas again you get this a different effect here because you can also get scattering orbits from such a space-time. So now, it's not just that the bound orbits are restricted compared to Schwarzschild. You also get changes, obviously, to the orbits of point particles around them. So here is an example of the effect of this cosmological expansion on the evolving orbits. So what you see here in the fairly regular blue curves that you see is what basically you get for evolutions, for radiation reaction in Schwarzschild, whereas the corresponding red ones is what happens when you consider the effect of the cosmic expansion. So here we've artificially made the cosmological constant rather large for us to be able to see these effects. And you see here one of the main effects too on the waveforms naman. So here you see in red the corresponding waveform for Schwarzschild, as opposed to what it would look like for a Schwarzschild de Sitter space-time where you do have this cosmic expansion. And so you see here that they dephase rather, eventually they dephase completely. So these are all representatives. So these are representative waveforms, gravitational waveforms coming from evolutions or self-force or radiation reaction evolved orbits in this space-time. One of the main physical consequences of this cosmological constant term is that rather unexpectedly, cosmic expansion tends to accelerate the plunge of the MRE down the horizon. So you see here on the plot, in the plots on the left, the decay in the semilattice rectum and the decay in the eccentricity of certain MREs, extreme mass ratio in spiral. So beginning, say, for example, from a rather large orbit with a semilattice rectum of 20, what you see here is the gradual decay in the semilatus rectum. In the case where the cosmological constant is zero, so you see here this curve in blue, and the moment you turn on the cosmological constant, you see here that its effect is primarily to accelerate, to make this decay faster, right? That basically means that plunge will be achieved faster whenever you have a cosmological expansion. So the expansion of the universe essentially makes the plunge happen earlier. Very similarly, you get an effect also in the circularization of the orbit. So, like I said, the emission of gravitational radiation, in this case as well, makes the orbit more and more circular. So you start here. We're starting with a highly eccentric orbit, and when there is no cosmological constant, you see that there will still be a circularization, but this circularization happens much more rapidly when you have cosmic expansion. So here on the contour plots on the right, what we're doing here is basically looking at circularization times and sorry, the time that the MRE spends on the LISA band before it actually goes into a plunge. So this is relevant for the LISA mission because it tells us, okay, well, how long do we expect these sources to actually remain in the detectable region of LISA? So this tells us, for example, if I start, say, for with an extreme mass ratio in spiral of a given eccentricity and semilatus rectum, the color scheme here tells us how long we can expect it to remain in the LISA band before it eventually goes into plunge. Um, so one of the ways we're extending this is by going to the strong field cell force. Currently, we only have radiation reaction calculations that really just incorporate the emission of radiation. This only incorporates the dissipative aspects of the cell force, not the full cell force itself. So technically speaking, all of these results will be invalid when the particle goes very close to the black hole. So now, similar to those research projects that I just talked about, we are also pursuing investigations of point particle motion, highlighting mainly chaotic dynamics. So characteristic one of the characteristics of point particle motion in curved spacetime is that it is these equations, the equations of motion, are largely or highly nonlinear, and nonlinear equations of motion tend to be rather chaotic, right? Um, this is, in particular, the motion of charged particles around black holes is quite important for understanding the structure and properties of relativistic jets. And so we've started a research program essentially trying to understand better the motion of charged particles around black holes. So here are some plots or some figures from work done I'm doing with an undergraduate, J.R. Oidem. So one of our favorite systems consists of a central black hole that's immersed in a uniform magnetic field. Astrophysically, this is not so this is not quite uh, this is not really an unrealistic system because you can imagine a uniform magnetic field set up by an accretion disk. So you can have a black hole and an accretion disk made up of charged particles, where the charged particles would be setting up this magnetic field around the black hole. So an example of the kinds of charged particle orbits of interest is what you see on the right here. So this very chaotic trajectory, and it's very interesting, is one that's essentially a trapped orbit because it's not a very energetic orbit. Such an orbit is bound; it doesn't escape to infinity. This is a representation. So this is a projection of the orbit onto the ZR plane. So the Z here is this this direction. Is the Z direction away from the orbital plane? Away from the in the direction of the axis of symmetry, pointing along the direction of the magnetic field. And so it's rather than looking at it in 3D, it's easier to represent this as this 2D projection here, and you already see that the orbit becomes rather complicated. One of the things we've discovered from this work is that when the energy of your charge actually becomes strong enough, The boundary that you see here actually opens up to infinity, and so that allows essentially the charged particles to be funneled out of the Newtonian center, therefore providing a possible model for the funneling of charged particles along relativistic jets. So JR has been very good in this work and has performed the full characterization of all the possible orbits that arise from such a system. This system actually, this work that you're seeing here, actually uses only a Newtonian center, so this is not in full relativity, but this was motivated by work that I had done earlier with a master student, a former master student, Joshua Bautista. So we published this work fairly recently, just last year. And in this work, we really considered a black hole that was immersed in a uniform magnetic field. So one of the interesting things about this system is that because of the chaos, of the inherent nonlinearity in the system, uh, notions such as escape energy, which would be typically well defined in you know in ordinary classical mechanics, does not become a well defined boundary. So here we tried to sort of characterize where this escape energy is. So the yellow plots here, the yellow color here, so this is in energy and distance away from the black hole. We sort of start a charge from a given position given by rho naught away from the black hole and give it a slight kick, which is represented by this energy epsilon here. And depending on what this energy is, what this kick is, it can either escape to infinity or get bound or remain bound to the black hole, or eventually might be swallowed or go through the event horizon of the black hole. And depending on those outcomes, we can track what that final state is and produce these so-called basins. So the yellow basin here corresponds to situations where we've given it a sufficient kick at a certain distance, say, and it ends up basically escaping to infinity. That would correspond to an escape scenario here. So you have this escape region that looks fairly regular, but if you zoom in, what you'll realize is that this is a fairly chaotic, and in fact, it has a fractal structure. And so this is, this is sort of typical of these chaotic escapes. So you have this nice situation where the escape energy is not really a very well-defined curve. And more than that, in fact, you get this self-similarity in this basin, the basin plot that you have here that has that in fact enjoys this rather peculiar property known as the WADA property. So this is something that we discovered some years ago, and then we published in this paper here. Um, so this is one of those things that, uh, again, like I said, other than just looking at, I mean, so one important uh, work in point particle motion tends to look at corrections to point particle motion via cell force. Here we're not looking at cell force corrections, but rather looking at test particle motion and understanding, its unique properties and how to characterize its chaotic behavior. Uh, and finally, the last thing I'm going to talk about today, also involving or revolving around point particles, uh, is actually quite an interesting sort of toy problem. So back in the late 1990s, 1999 to be precise, Veronica Hubany, who is a famous string theorist now, was then an undergraduate. Uh, uh, she was able to make this prediction that somehow, if you consider a black hole that's very close to being an extremal black hole, whose charge is very close to being the maximum possible charge it can have, you can consider throwing in a small charge into it, and in that process, overcharge the black hole. So an overcharged black hole, so in overcharging the black hole, what you do is actually remove or sort of destroy its event horizon. So so these Reisner-Nordstrom or charged black holes that I showed you earlier, they come with a bound. Q can only be less than m.
So its charge can be needs to be less than its mass for it to have a horizon. And so you can imagine what happens. Okay, if I keep on throwing charge into it, Uh, what happens to the space-time as the charge of the black hole gradually approaches this extremal limit? So there was early work by Bob Wald looking at what happens when it's already at extremality and when Q already equals m. That situation still represents a black hole, but he found there that it was impossible to actually throw in a further charge that will cross the horizon. So that seemed like the end of the story, but Cuban dug a little deeper and considered, well, what if the charge is not actually the extremal charge? What if it's slightly less than the upper limit that's allowed for a black hole? And then she discovered that, okay, well, it turns out that you can still throw charges into a black hole and possibly make it go beyond the limit. Now, this is problematic for a number of reasons. Probably the biggest conceptual reason would be, where does the entropy go? So the entropy of a black hole is represented by the area of its horizon, and in this process you basically have what seems to be a violation of black hole thermodynamics. So it was long suspected that this would be prevented by cell force and radiation reaction effects, because when Hubany looked at this process many years ago, she did not incorporate cell force effects. Some recent work by Source and Wald, however, has shown that this in fact is not possible if you considered higher order effects, which do include cell force and radiation reaction. But for some time, the question was always, well, what is the effect of cell force and radiation reaction? Does cell force, in fact, um, uh, does it serve as a cosmic sensor, so to speak? Does it prevent the creation of a naked singularity? And so some of the work that we've done in this along these lines was to really compute the effect of the cell force on these overcharging orbits. So in this work with Peter Zimmerman, who was a master's student uh, back in Guelph when I was still a postdoc in Guelph, we embarked on this very difficult project of computing the cell force for these overcharging orbits, and then we discovered, in fact, that the radial cell force, true to what was believed, uh, is always repulsive, right? And in fact, for all of the orbits that we considered via Monte Carlo simulation, was sufficient to prevent the overcharging process from occurring. So this is a nice paper. I really like this work because it sort of provided a completion to the story that people had already believed for so long. Um, Much more recent work that we've done here in the Philippines from my group was work done with PhD students. So here we really just were being quite playful. We asked, well, okay, so now that we've sort of closed the door on four-dimensional overcharging, well, what happens if we considered higher dimensional black holes? And so Carl Revelar, who was a PhD student back in 2017, uh, looked at this scenario where we imagined a non-rotating higher dimensional black hole, and we looked at, okay, well, what happens to the Hubany scenario? What is the impact of these extra dimensions on the Hubany scenario? And one of the surprising things from our calculation that arose from our calculation is it seems like as if the higher dimensions actually make the process more difficult. So the plot that you see here shows you, so this delta E, you can think of this as basically the allowed energy the allowed energy in the space of overcharging orbits, the allowed energy in the space of overcharging orbits. So the smaller this is, the narrower this space becomes. And so you see here that in four dimensions you have a fairly big, well, it's still small because it's 10 to the minus 1 based on the parameters that we used. But what's important is not the magnitudes, but the overall decrease in this delta E, um, uh, um, this space of this space of overcharging orbits that's allowed as you increase the dimensionality of your black hole. So this is a surprising thing, and this has ended up becoming one of our most cited papers coming from NIP, and it was worked by a PhD student. So I'm particularly proud of it. And so this is a kind of thing where playful thinking actually gets you um, quite a bit of mileage. So we initially did not think that anything interesting would come from this. And we were surprised that nobody had considered overcharging in higher dimensions. So it was just by merely asking this basic question. And the calculations for this was actually quite simple. I was able to write the paper in about 2 days only, and so yeah, it was just this is one of those things where you ask a simple question, you do simple calculations, and you get an interesting result that turns out to be quite fruitful. Yeah, so that represents a sampling of the work that we do in my group. There's obviously a lot more uh, that we do in black hole physics, but many of these works have sort of grown from the studies that I've been able to show you here. But most of them, much of them revolve around considering point particle motion and corrections and novel aspects of point particle motion in curved spacetime. All right, so I suppose I could end here. So the key takeaways I hope that you were able to get from my talk are that well, advances in astronomy and particularly instrumentation really have brought us to this golden age of gravitational physics. So nowadays, so GR is no longer a backwater subject, but it's really an integral part of strong field relativistic astrophysics. Um, so I also tried to emphasize that although the theoretical modeling that supports these advances tend to be very computationally intensive, there still are a lot of good questions that can be asked by, or that can be answered by considering simplified models, particularly point particles. And this is what we've been doing in the group. Um, my group in particular is committed to continuing this exploration, and I hope we continue to get support from the appropriate funding agencies. So thank you very much. I'll leave you with this final slide because much of the work that we are able to do is certainly not possible without the efforts of my very enterprising and very hardworking students. So maraming salamat po.
All right. Thank you very much, Ian. Uh, Fascinating talk. I guess I would like to ask questions first from the audience because I have a bunch of them. And any questions from the audience first? Okay, so I'll start. I have three of them actually. So uh, when we start thinking about theoretical physicists, the way people would start thinking is, hey, these guys are just use pen and paper, and then on the other extreme, you were saying, actually, when you do numerical relativity, you actually need probably supercomputers to run these things. Where does your work lie in this spectrum, and what do you usually use?
Right. So yeah, it's a good question. So I think I'm in between both of those extremes. So I'm not a numeric relativist. So although again, like I said, one of my PhD students is fairly ambitious and he wants to head towards that direction. I'm not trained as a numerical relativist. So I don't use these. I don't need the large supercomputers just yet. On the other hand, I'm not a purely pencil and paper person because I do many of the things that we do require at the very least integration of ordinary differential equations, integration of simple partial differential equations for these wave equations. But they're all sort of in this regime where I can still do things. I can still run things on a laptop or on a PC. So they're not quite. So oftentimes, like for example, for the chaos work that I showed you earlier, uh, that's sort of a project, a problem that's um, uh, uh, prime for parallelization. So occasionally I will ask my student, okay, we'll use all the cores of your laptop efficiently. So kahit 4 or 8 cores lang yan, pinapagamit ko. But that's the extent of it. I don't go beyond that. Uh, it would be nice to push towards numerical relativity. In fact, that's kind of, I mean, if I were to have a goal in the next few years, it would be to try uh, uh, to make contributions to numerical relativity because that's really where all the there are many open questions that remain there. Uh, so to some degree, the kinds of things, the kinds of questions I tried to ask and to solve, uh, uh, they could have been solved maybe by people like in the 1970s or 80s. So the challenge for me is to try to ask creative questions that um, are better addressed because I have a personal computer, right? And so much of this work, for example, like discovering, for instance, uh, uh, different ways of characterizing chaotic behavior, that's something that would have been very difficult to accomplish without computers. Cell force calculations, for also as another example. So this is semi-analytic work. So a lot of the things, there's a lot of analytic work as far as setting up the expressions go. So you have to do a lot of analytic work to know what you're supposed to evaluate. But then if you actually want to produce a number that you then have to incorporate into a model, kailangan mo ng mag numerical calculation. So usually this comes in the form of evaluating special functions and performing infinite sums, doing convergence checks as well. So I would say that I'm a semi-analytic guy, right? Not fully numerical, not fully analytic. And I have colleagues. So most of my colleagues in NIP are strongly analytic. So I'm somewhere in between. Um, now, and again, this is kind of where the field is also going. I think it's also where most of science is going anyway. I mean, it's very difficult if I were to remain in doing fully analytic work, I'd be able to answer much fewer questions, if any. uh, so yeah, so
All right.
that's a very long answer to your question, but I'm somewhere in between.
Thanks, Ian. Gladys has a question. Gladys?
Hey Gladys,
Yes, thank you. Oh my gosh. You've done a lot of work, and I learned a
thank
lot.
you.
So from self force, right? Self force motion, and then chaotic point particle motion, and I learned that there's you can overcharge black holes. But
Yes.
I have this very naive question: how long does a black hole last?
Oh, very, very long. So much longer than the age of the universe.
Okay.
That's an excellent question. So one of the things we did not actually cover in my talk is the fact that black holes actually evaporate. So 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 Stephen Hawking became famous for for many
Yes.
things. One of his uh, biggest claims to fame was his discovery that black holes actually do evaporate. So even if you look at a
Mhm.
quiescent black hole, like a simplest black hole you can think of, if you consider the so-called quantum fluctuations or fields outside the vicinity of the vicinity or in the vicinity of the horizon of the black hole, you can derive that in fact um, um, uh, uh, um, there is the so-called Hawking radiation that's emitted by this black hole. And because I mean, there's always going to be quantum fluctuations outside a black hole. This essentially leads to the shrinking of the black hole in time. But this is a very slow process for astrophysical black holes. So the the time scale of this emission, so the time scale of the shrinking, is actually proportional to the mass of the black hole. So I mean, the question you asked is actually quite interesting because uh, the very small black holes. So there
Yes. Mhm.
are sort of microscopic black holes that people were afraid of when CERN, when the Large Hadron Collider was still hadn't turned on. So one of the worries that some physicists, in fact some lawyers, were very concerned about was the possibility of creating microscopic black holes in the LHC. So just as, for example, large black holes evaporate very slowly, and so
Mhm.
these large black holes that I talked about, the black holes that we see, that LIGO sees nowadays, um, yeah, these black holes will exist for all time, practically for all eternity. But the microscopic black holes, they decay very very rapidly because they're very small, and the time scale. So the how fast these things decay basically go as depend on their masses. So smaller black holes evaporate very quickly. Larger black holes take forever essentially to evaporate. But yeah, all black holes evaporate. That is one of the one important fact of black hole physics.
One more thing, Ian.
Sure, ma'am.
So please don't please encourage your graduate students to present this coming 42nd APAMS, right?
Sure,
Your case,
yes. Yeah.
please submit a paper, okay?
Sige
And
po,
then
I'll
yes,
try to I'll try to get more work from them. But I think they'll be very eager naman to present their
yes,
results.
and then
Yeah.
so that we can have really a session for that.
Yeah. Okay.
Okay. Yeah, congratulations again. But I have a meeting by 10, so
Thank,
I might leave soon. Thank you
thank you.
very
Oh,
much, Ian.
Yeah. I
thank
just have to point out that I probably forgot this in my talk that uh, I'm really quite grateful for the support that I've gotten from UP Diliman, and from the Balik PhD program in particular. So I think more than anything else, Balik PhD has been very forward-looking, very liberal, very generous in its support of work such as this, which is kind of hard to sell to agencies outside of UP.
That's
But and so I was funded way before the hype, way before the discovery of gravitational waves, right? So when I arrived, it was announced. The discovery is made fairly recently, but I'd already gotten the go signal for the work that I was proposing. Like, and again, this is for gravitational wave work that will be relevant in the 2030s. It's not even now, because my much of my work is for the modeling of low frequency gravitational waves. So I'm really quite grateful for um, the fact that UP OVPAA does not restrict itself to you know uh, allows blue skies research, allows theoretical considerations such as the ones that I'm pursuing.
excellent. Actually, Giselle is here maybe to
Ay,
talk a bit
okay,
about that.
all right.
But let's go to
Thank you.
Mario first, and then Gisela for the questions.
Hello,
Hello,
yeah, Ian. This is
hello.
Mario. I'm very glad I attended this meeting. Although I think this is one of the talks that you need some prerequisites, before,
Yes.
because I was trying to draw from my like physics 21 and physics classes from UP way back. But my question is about, is there a critical mass right now in the Philippines for this type of research and studies? And you mentioned about like support from funding agencies. Do you think you are represented in the table, or at least people who may be friendly to these ideas that perhaps could bring you some resources so that you can pursue this line of study for yourself and for your team, and to grow it in the Philippines?
Yeah. So that's right. So I'm. Thank you for the question. I would say that UP has been very supportive. I cannot say anything bad about UP. In fact, I would say that this kind of work, it's not just my work. Work of my colleagues as well is of a similar nature. But one of the speakers today would have been Dr. Jason Cosme. Is one of my recent colleagues in NIP. He also pursues rather theoretical work, although he has much more experimental connections with experiment is stronger for him. Um, but there are other people like Dr. Eric Galapon, who works on quantum foundation. All of us have sort of found a welcoming home in NIP and in UP Diliman, which we're actually very, very grateful for. I don't think so. To your first question of whether there's a critical mass, there certainly isn't. I'm at the moment. I'm currently, well, maybe there's maybe one other, but I think I might be the only active relativist in the Philippines. Uh, I recently mentored a PhD student in Dr. Reginald Bernardo. He was the first PhD in general relativity from the country, but he's now a postdoc in Taiwan. So I'm working very hard to get him back to join our group and to sort of try to get to that critical mass that you talk about. So I've been asked this before in other venues of what I dream for the Philippines, when I get to retire. For me, it's not so much that so obviously there is uh, I work towards contributing to the field and growing and making discoveries and these drawing insights from about black holes in black hole physics. But for me, I think the bigger goal is to really see a thriving uh, gravity community or theoretical physics community in the country. And even there, there's still quite a few. There's not enough of us, even if you just consider physics in general. So, uh, I am hoping that other universities will be as encouraging as UP Diliman has of me and of my colleagues. At the moment, I'm the only one doing gravity work, but I hope to recruit more back to UP. But again, these days it's fairly easy to actually recruit people. I have to say, because again, like I said, uh, UP has effectively insulated us from the demands of the OST and from other funding agencies who may not be um, um, as open-minded about the topics that excite me and excite many people. So I think there's still a fair amount to go as far as making these funding agencies realize that blue skies research, these kinds of research, is actually important and cheap, very very cheap compared to uh, orders of magnitude cheaper than than what my experimentalist colleagues would need to pursue their own investigations. Sa amin kasi, yeah, like May says, it's just paper, pencil, and computers. Computers pa nga, that's something that's most students already have anyway, and again, it's really about the challenge is really about posing creative questions that you can address with paper, pencil, and a computer. Uh, 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 right. I'm hoping that we continue to get support from the funding
Yeah.
agency. So I've had success in one respect but this is because I won the outstanding young scientist grant from the NAST. So that came with a grant. So that's a DOST grant, but I haven't really applied for anything outside of UP because I've sort of been uh, UP has spoiled me and has spoiled colleagues of a similar um, with similar theoretical interests. Kasi okay na sa amin eh. Uh, we can produce quite a lot with the funding that UP supplies us.
Thank you for doing what you're doing, and let us know at PAASE how we can support you. I mean,
Ay, sure. Thank you po. Yes.
yes, of course, yeah.
Thanks. Gisela?
Yeah, thanks. I came in late. May,
Hey,
thanks
ma'am.
for organizing this. And I'm just so happy to hear Ian say what he just said about support from UP. And well, it makes my day. So he's one of those outstanding PhD faculty we recruited. And Ian, as all things in physics, we're talking about rates, acceleration, and speed at which you can grow that critical mass that Mario is asking you about. And there are other programs in UP, OVPAA programs that we set up to help you. I know with paper, pencil, and laptops, it doesn't cost a lot, but you can actually, shine the rest of the world's your stage, and you can continue to grow your flock with collaborations with PAASE members who are also in related fields, as well as with collaborators in Taiwan and other advanced countries. There is the
Mhm.
Cooperate program where you can send your
Right.
master's and PhD students to your trusted collaborator abroad. And then that person comes back. If he's not yet faculty, then you could get him as a postdoc because postdocs are so few in UP. So
Yes, that's right.
we could try to get that postdoc to well do more research in collaboration with your foreign collaborator,
Yeah.
and that's how it grows.
Yeah.
And I think that NIP is the single most I must say it, and I've said it over and over again, most outstanding world-class institute of university. And you have your faculty to to thank for it. I think there's been a tradition, and it has started with the time of Roger Pasadas. You know, Joey Magpantay, he would publish papers just using the creative research grant.
Yep.
Uh, and we expanded that. And even before he got, you know, he completed the grant, he would already publish, and that would then allow him to just go for the next creative research grant. But now it looks like it doesn't work that way. You
Hmm.
know, it's turno again. But that was not the idea. As
Yeah.
long as you're productive, you have a publication, you should be entitled to the next one, and that's how I wanted it to be. But anyway, you know how it is in UP, turno, fair and square, but it's not fair. It has to be a meritocracy, right, May? You have to thank your former directors, our dean, Cesar Saloma, who built an institute that is uh, something we can be proud of today. So thank you very much. Now,
Thank
I
you, ma'am.
just came, came in late, and all of us are fascinated with black holes. And I just wanted to know the latest on it. And I wondered if you touched on this. Fastest growing black hole ever seen is devouring the equivalent of 1 Earth per second. A newly discovered black hole with a mass 3 billion times that of the sun is growing by rapidly consuming matter and has powered the most luminous quasar for 9 billion years. In 2020, astronomers reported the closest black hole on Earth to Earth, located just 1,000 light years away in the
Hmm.
HR 6819 system. So anyway, I'm sorry, maybe I missed this, so no need to answer if you already started your talk with this. Thank you,
Yeah.
Ian.
Thank you, ma'am. Thank you, ma'am Gisela. So I didn't talk about those recent black hole discoveries, but the idea that AGNs or active galactic nuclei who swallow stuff up and literally light up the sky. Uh, this is this is one of the early examples that I showed before. So in fact, one of the sort of I say this in my physics 10 class. One of the most ironic things about black holes is that although they're black and in principle they absorb everything, they end up becoming the brightest objects in the sky uh, because they are the most efficient burners of gas and stuff in its vicinity. So when things fall down a black hole, when there's enough gas that you can sort of get through its event horizon. Before it crosses the event horizon, you actually burn up these stuff, and you end up really lighting up the sky as a result. So active galactic nuclei is what they were called before. I mean, they're still called these things now, but these AGNs by and large tend to be or are the result of black holes burning gas in its vicinity. So the examples that you cited, ma'am, these are the most recent ones, the most popular ones, but there are so many of them now that different, astronomers of different groups have their own special system that they're looking at because each represents like a special system that needs to be characterized, needs to be studied uh, in all different frequency bands and using both a combination of infrared, X-ray, and sometimes even optical. And nowadays we can also look at them through gravitational waves. So the really exciting part is that you get all these you get this accelerated advance in the field as a whole because it's not just gravity people who are interested. It's really it's become sort of part of high energy astrophysics. So astronomers, uh, uh, in some sense, gravity is no longer just a theory subject. It's really an astro subject, and we get to now answer questions such as is Einstein's theory really correct in these environments, in these regimes where gravity is very, very strong. So up to this point, we had not been able to probe this regime. Einstein's theory has been very successful for things like uh, motion in the solar system, the strongest na siguro was the detection of a pulsar by Hulse and Taylor in the 1980s that won them a Nobel Prize in the 1990s. But other than that, there have been terrestrial and weak field tests. Been very successful. All Einstein's has passed all of them in with flying colors, but there was always this prevailing question of tama ba talaga siya all the way to very very strong gravitational fields, and so now we're beginning to see that region, that open field being broached because of the advances in instrumentation and astronomy. Now, going back to your cooperate, ma'am. So I'm one of my PhD students actually will be applying to that. I think that's also one of the great things about the cooperate program because we've looked into this a bit, and it's an opportunity for someone like my PhD student who's very good, very talented, very hardworking, uh, but wants to work in an area that is not quite my expertise. So I do have so my expertise is gravity, but I don't do numerical relativity, so I don't. I mean that is a technical, a rather technical field for which just GR knowledge is not enough. And so since I have friends in some parts of the world, I would like to be able to send him there, at least for him to be able to do his PhD dissertation in part with these other groups who have more expertise than myself. So this is one of the ways one can sort of I think it's a very I hope we get in. I hope I hope he gets to go. But if he does, I would say that that would be a very successful use of funds because it would um, really expand our knowledge base here. It will allow us to train students even though in fields that may not necessarily be uh, uh, fields where we have expertise in. So I'm very excited about that.
Sure. Thanks, Ian. Maybe just one last question, being the moderator. I'm gonna
Yes,
ask
of
this.
course. That's your prerogative.
So that question is, so for example, you showed the plot, the last plot that you had with Carl, and it spans several orders of magnitude in energy, and you actually talked repeatedly about making sure about calculating the noise baseline and all that. In in what do you think? With the things you're churning out, the theoretical stuff that's being churned out right now, and once let's say LISA launches, uh, would how sufficient are the current instrumentation uh, at this point in terms of being able to capture a lot of the theoretical predictions that you have, or even as well as how would the data be handled with things
Right,
coming in? Where are we now, and how much more does the frontier need to be pushed to be able to
right,
capture all these things?
right. So yeah, that's a great question. So I honestly don't know how the data handling will be managed. So I'm currently not yet part of the LISA collaboration. Reina and I, so Dr. Reyes is a new colleague in NIP as well. We are hoping to apply for membership, if not this year, then next year. Uh, so my friends from my PhD days are currently occupying the leadership of the LISA consortium, and they've been inviting me for a long time because they want Philippine membership. And so now, but I've been reluctant to join in because I'm not a data person. I'm not a data analysis person. And but now that Reina is on board and she is very interested in gravitational wave data analysis from her cosmology experience, we now sort of have a legit team. So it's us and then a bunch of really talented grad students that I'm now fairly confident that we can contribute meaningfully to the LISA consortium. So we will apply to that. So we will learn more about how they will handle data. But I imagine so. But so it the reason I'm not entirely sure is because so this is actually going to I imagine this is going to operate much like how our current satellites operate. So they're probably going to be uh, telemetry on the LISA satellite, but I'm not sure if it's going to be shared to people outside the collaboration. Uh, so at the moment, LIGO does release all of its data as soon as they make an announcement. So I imagine that Lisa will operate in a similar fashion. Um, but again, unlike LIGO, Lisa is more time bound. It only has a lifetime of about uh, 5 to 7 years, possibly, and then it will be decommissioned. So during that time, it will be making a lot of measurements of all sorts, basically, and it will not be able to descend time because it's not a directed kind of it's not a directed satellite, right? It's not a directed telescope. So it will just fly as a constellation, just making measurements, as many measurements as it can, and then in the end, we'll just get one giant noisy data stream. And then the idea will be to find as many signals as we can in this very noisy data stream. Unlike LIGO, Lisa is expected to have a significantly higher, it will be significantly noisier than LIGO. And so that's why the challenge is much bigger um, uh, for Lisa. On the other hand, though, because diba, when you're trying to find signals from noise, um, signal to noise ratio is really what's it's the key figure, and because the kinds of sources that we're interested in with Lisa are very long time stream, long time series. You have a much longer integration time, so potentially increasing um, the signal more. And the hope is that if we have good enough models, then that are sort of that can maintain fidelity with the actual signal for like 7 years. There's a lot of ifs there. So, but if you have, in principle, if I were God and I can say, okay, this is a correct representation of actual physics of the actual physical scenario, then then in principle I should be able to use that to really find the signal from the noisy data stream, just because my integration time is significantly longer than the integration times that LIGO has. So LIGO's signals last for seconds. It just really less than a second. So the blips that you see that I showed you at the beginning were I forget what the longest signal. The longest signal was a neutron star binary, but the black hole ones are really very quick, and so there the for you to get a signal, you need to have a very strong signal above the noise, because the integration time is so less. For Lisa, it's different because we expect them to be weaker. Uh, the noise is going to be much stronger. So the to for this whole mission to succeed, it is essential that we get a signal that's very accurate over the entire mission lifetime. And so that's why models with cell force and radiation reaction are really essential for the whole task. In the meantime, we don't have data, so the game has been to produce mock data. So there are these mock data challenges. I've been inviting Reina to try to partake in this because she would be um, uh, uh, more qualified to pursue these kinds of work. Um, but the idea there is to, I mean, and these are sort of like games that are being played by the consortium. So they essentially generate and they bury signals in simulated noise, and they challenge the different data analysis groups to sort of find the signals in their simulated noise. And sometimes they will even put something without the signal to see, if you get a false positive. So these are sort of so at the moment this is really what the entire community is gearing up towards for eventual launch, hopefully in 2034. So I don't know. I keep on telling my students, 2034 is something I will look forward to. I don't know how old I'll be by then, but uh, Lisa was already promised to me even as a PhD student. They were saying, okay, it's going to launch in 2015. Then 2015 is no past. Tapos naurong siya to 2034. So I don't know what's going to happen. Obviously, it's largely a function of I suppose the incomes, the economies of the primary countries that are pushing for these projects. Uh, but it's looking like Lisa is really in a good position now. It launched so-called Lisa Pathfinder, which was a test of how well they can control or minimize the noise in because these are lasers in a so you can imagine they're basically satellites with lasers pointing out in two different directions that are to form a satellite. So they launched one of these already to control basically, or to see how much they can control the laser noise from one of them. And quite remarkably, they were able to beat the noise floor by an order of magnitude. They were surprised at how good the technology actually worked. And so once that was this was, I think this was done in 2016 or 2017. Because of that, NASA and ESA have been very very supportive of Lisa. So I think it will fly because they were able to demonstrate that the technology actually works. And so now, obviously, there's still a lot of challenges that remain because you have to launch 3 of them, not just one. Um, but yeah, so there is a lot of momentum behind the project. Now, the James Webb Telescope took priority now, so a lot of the money has now gone into James Webb. James Webb is the most exciting thing these days, and I have some grad students in the states, former grad students in the states, who are trying to get involved in the James Webb Telescope. But I think Lisa will be the next big thing.
All right. Thank you very much, Ian. Thank you also to our audience who's been here for 2 hours. So thank you. So I'll stop the recording now.